maybe the place to start is to tell you guys a little bit more about Wellframe. So we are a Boston-based venture-backed digital health startup focusing primarily on care management. And for anybody not really familiar with care management is our attempt to try and take care of complex patients when they're not in the hospital. Let's see if this thing wants to. So this is our goal. We want to bring the highest standard of evidence-based care to all of those in need. And I want to drill down on a couple parts of this. The first is the evidence-based piece. So whenever a patient is in the hospital, a lot of the decisions that are being made on their behalf are being made according to guidelines. And those guidelines are based on clinical research studies, which look at a specific clinical scenario and figure out the optimal action, and then measure the sort of short, medium, and long-term outcomes that you can expect out of taking that action. This is very helpful until the person leaves the hospital, and then they no longer have these guidelines to help them navigate making health decisions. The other part of this is all of those in need. So you might have seen some of the talks earlier today from our friends at Lyra, and a lot of those approaches really focus on depth over breadth. I think here we're trying to reach the widest possible audience we can. We have everything from 18-year-olds with severe and persistent mental illness, all the way to 85-year-olds with congestive heart failure, and pretty much everything in between. So how do we do this? Well, the first thing we do is we take those guidelines and we try and interpolate them to give us day-by-day little tidbits and distill them down to what we think are kind of the atomic elements. Then we take those and we give them to our users, and then we can combine them across different diseases, diabetes, hypertension, to give them a relatively custom approach, but at the same time give them those granular day-by-day instructions they need. This is in the form of a task list, which they can get on their smartphone. This could be medication reminders, physical activity goals, educational content about their disease. Then the other piece of this is the clinician side. So we provide a dashboard for our clinical staff, which can be doctors, nurses, care managers. And this allows them to see all of the data that's coming off the phone so that they can keep up to date on what's going on with their patients, as well as message them through a secure HIPAA-compliant messaging platform. This is what care management looks like today. So if you're a complex patient and you're not in the hospital, chances are you'll hear from your care manager about once every 3 months. This is really just not efficient enough. We have too many people and too few clinicians. So how do we make this more efficient? Well, what we want to do is we want to take those periods, those 3-month windows, and we want to make sure, because we have relatively little visibility into what's going on during those windows, we want to be able to see everything that's happening. So we're starting to get data off the phone. We also can have the messaging back and forth. But really the key to making a care manager efficient is just getting every piece of data we can. We would ingest that, and we would make sense of it, and then that would allow us to help the care manager triage their patients. This, from our just messaging alone and with a little bit of use on the phone, we can start to get sort of a 3x improvement, but that's nowhere near what we need to actually cover all the patients that require these services. So with that in mind, we started saying, how do we get more and more data to leverage to use against this? So we started in the kind of obvious place, which is, let's just get the data that users are already putting into their phones. We can get message data, we can see what tasks they're completing, and we can also get a sense of which activities they're performing on the phone actually lead to better outcomes on their part. So then we wanted to extend this and start to see, where are they spending time in the app? Are they really reading the content that we're giving them? Who's doing messaging? All the little details to kind of tell us what their experience looks like. We did the same thing with the care managers. When care managers are about to message a user, we want to be able to figure out what is the data that they're looking at that paints that clinical picture that's going to allow them to do an outreach in a meaningful way. And of course, we need to do things like API monitoring and just sort of standard stuff. But all of this right now really doesn't help us make the care manager that much more efficient, because most of this isn't clinical information. This is just essentially refining the product, improving the experience, improving stability around the API and like our back-end performance. So then we thought, okay, what we need to do is we need to plug into the clinical information to figure out what the healthcare system already knows about these people. What happens to them while they're in the hospital? What does their primary care provider know? So we started to try and plug in and integrate there. Well, we always joke about this in the office, that if you want to break into the EMR industry, it's only going to take you a few decades to get your MVP up and going. And we got a little taste of that when we did this because there were so many different data types that we had to manage to just start to get that 80-20 of clinical information we needed for downstream decision making. You know, the first thing we tried was pharmacy integration. A lot of our patients have 20 plus meds. We don't want them to have to enter them manually because that's super error prone. If we can ingest all of that for them, hopefully we can increase medication compliance substantially, start figuring out scheduling and all of these things. And we realized how onerous this was the first time around. But then we started trying to do this more broadly, and then things kind of went haywire. So it's worth taking a step back. I can sort of give my biases, because when I was looking at this, I was coming from a genomics background. And you know, genomics, in retrospect, is a very classic data science problem. It's basically everything is in batch. There's no concept of streaming. Your data set is just sitting there. ETL is pretty straightforward. You just take that whole thing, drop it in a big machine or your cluster, and you're pretty much done. And the data is super homogeneous. There isn't really a whole lot to manage. So, I mean, obviously the first thing we all think of is scale, but I knew from previous experience we were nowhere near the scale that you would need to be at to actually start breaking just because of load. What was pretty apparent was the number of data types we had to manage and just the amount of bookkeeping we had to do was causing a lot more problems, and this is something that we hadn't really thought through. And the last part is, genomics at the end of the day is a scientific endeavor. If you have to make simplifying assumptions about your data types, you can just write off some of it and say, I don't know what's going on there, it's noise, it's just corrupted data. Healthcare, we can't do that because you know, this is all about clinical trust and we're making decisions that affect people's lives. So we need to dot every last I and cross every last T and make sure that our data is exactly what we think it is. So the big question was kind of how to handle this. Well, the obvious thing to do is we're starting to get more and more data. Let's just let our data scientists loose. And that was kind of where we started. And that was with the understanding that at some point they're going to hit a scale bottleneck. And then we'll get the infrastructure guys involved. And I think that this kind of division is something that we're all used to. Data science lives in one place. It's one group of people. Infrastructure is a totally separate one. And this divide becomes very, very important. So today I'm going to be talking about basically infrastructure and upwards. We actually have a lot of work that we've done infrastructure and downwards all the way to the cluster level. Jeff Warren, who's our lead infrastructure engineer, is in the audience today. So if you have any questions, please feel free to come and grab us afterwards. He's also writing a series of blog posts for Mesosphere on our experiences with Mesos and DCOS. I think it's also important that, also in retrospect, looking back on this, I realized that this division actually works really well when scale is your only bottleneck, right? You let your infrastructure engineers build out a platform, data scientists just use it, they never really need to talk to each other, and things work beautifully. So where does data science start? Well, data scientists, they're great at finding needles in haystacks. Until you hit that infra bottleneck, they're pretty good just on their own. And they're really fast if your ingestion works well and you can get things into a data frame. They're pretty much golden after that, and they're just going to start turning out a steady stream of insights if your ingestion works. I think it's worth, you know, data frames have very quickly in the last few years become sort of the common currency in data science. And we all know that they're very performant. I remember the first time I saw the Spark numbers where they showed that data frames were much, much faster than RDDs and in a language agnostic way, and that was pretty convincing. And they're obviously super, super convenient if you're doing data science and a data science workflow. The issue is they're not type safe, right? And I'll come back to this a little later, and I think that this speaks to kind of where we see data science fitting into the larger organization. So how did we start with data science at Wellframe? So we were doing everything with Python, Panda, DataFrames, which is a pretty standard setup. We were doing everything in a one-off way. So we get a new data source like app usage data, and then we just start writing a lot of scripts that basically ingest that. And this is heavily manual. So now when we get the next set of data, be it say our dashboard usage, we're going to reinvent the exact same type of pipeline. The bigger question here is kind of like, what was our goal with this? What are we hoping to get out of it? Now, this is where I kind of want to take a step back and say our goal is to make those care managers more efficient, right? But at the end of the day, what data scientists are producing is they're producing insights, and those insights could be reports and graphs, they could be academic papers. But at the end of the day, we need the data to be, and the insights that they're gleaning, not to just inform features, but to actually be the features. The other problem we quickly became aware of was the diversity issue. We were seeing too many data types. This was all being cleaned and QA'd manually, and this was slowing us down. Our data scientists were spending all of their time just trying to get the ingestion working, and they were getting totally drowned in that. And they weren't having any time left to focus on finding the insights. Instead of finding the needle in the haystack, they were spending the whole day just moving the haystack around. So this is when the infrastructure guys got involved. And the first thing they did was they went and looked at all those things that were being repeated by the data scientists over every different piece of the pipeline, and they quickly libraried that away. This became orders of magnitude more efficient, both in terms of developer time and in terms of performance. The other bonus that this yielded was this was being done in Scala rather than Python. So we take in a bunch of raw data, it goes through this library, and out come a bunch of Scala case classes, which is basically one stop short of having a DSL on which to build very robust features. Which kind of leads into the part that I felt was really the most appealing, which is, okay, we know we're having a bit of a bookkeeping nightmare in terms of taking in all the data, and we don't want to have to manage all of that complexity by hand. And one thing that isn't built into a lot of data analysis is regression testing. So as we move forward, we want to make sure that things aren't breaking that we left in our wake. One way to do this is to just go and pepper assertions through your code and then hope that that will sort of plug all the leaks. But we all kind of know that that's going to break down going forward. And this is where the type system really kicks in, because this type system will take all the invariants that we care about and will force them continuously going forward. So at this point in this week, I'm sure this looks pretty familiar. So the first thing they did was they took Kafka and put it between the data sources and everything downstream. We had some Scala consumers, which then yield case classes. But the question is, where was this leading us? So now we could safely ingest all of our data. The QA was like rock solid. We know exactly what we have. But the problem is the data scientists don't know Scala, so they can't take advantage of these case classes that are coming out of our library. And it's a bit of a stretch to ask them to just completely give up on Python, because Python has much better support for data science than Scala does. Okay, so now we've solved one problem, but it seems like we've come to an impasse. And what we've done is we basically ran up against that wall that divides data scientists from infrastructure engineers, right? And the question was, how do we get around that? Because we still want to build features, and we want to use all of this data for downstream purposes, right? We don't want to just ingest it and let it sit there. So actually, I had this conversation with Alexei when we were talking about this a few months ago, and he told me that what Nitro is doing, I believe, is they're hiring data scientists that either know or are willing to learn Scala. When I heard this, the first thing that came to mind is, where do you find such people? That sounds like a unicorn if ever I've heard of one. And so if he was willing to help us find these, I would certainly be in favor of that. If anyone in the audience fits this description, please come and see me afterwards. In the absence of finding unicorns, we had to come up with something different. And so for us, we started to use Spark not as a means to handle load, but as an abstraction layer to separate our infrastructure from our data science. This had the plus that the data scientists got the data frames they wanted. It had the downside of, well, that type safety that we fought so hard to get in ingestion is now getting thrown away the second we put this thing in a data frame. And the one thing we'd done in the meantime is like, okay, we're ingesting all this data. What are we going to do with it? Let's put it in a nicely schematized database and just dump it there until somebody can figure out what to do with it. Okay, so now we take Spark. We give our data scientists the Python data frames that they want, the PySpark data frames. Okay, but now where do we go from here? Because now we're back to this question of, if we really want to build robust features, we're going to need end-to-end type safety. We've solved the ingestion question, but we still haven't gotten to how to build features. So I think a lot of this is kind of what we're used to, because we're used to data scientists being siloed away from production engineering. And what usually happens is a data scientist writes some code, they find an insight, and then that insight is delivered to someone like a PM. The issue then is the PM takes this to an engineer and then asks the engineer to build it, and then the engineer writes some code, which is probably pretty similar to what the data scientist used in the first place, and then they go and deploy this feature. So the obvious question is, what is it going to take to short circuit this? The first thing is more tests. Data scientists definitely don't write as many tests as production engineers or infra engineers. Okay, fine. I think we can get over that one. Structuring code. Okay, you can't script as much. You need to start thinking about coding for reliability and maintainability down the road. Okay, fine, we can restructure the code, but this was the sticking point. They were working in Python. How are we going to get them to work in Scala or something similar? This is kind of where we started. Now, admittedly, this is not the best representation of Panda's code. You're probably going to see a lot more slicing and a lot less chaining if you were to actually see Pandas being used in the wild. But the point is that it's not unimaginable that you could get your data scientist to code something that looks like this, right? And we actually already had, because we were asking them to use PySpark DataFrames. And so now this is starting to look a little more familiar because it's Spark. And Spark is basically heavily influenced by the Scala collections library. So then the question becomes, why can't we just take this and turn it into a Scala or Spark data set? We get all the type safety we want, but at the same time we'll get the performance and the semantics that the data scientists are used to from using DataFrames. All they need is a couple little type declarations peppered in there, and then they can take advantage of all the ingestion case classes that we produced and just code directly into that code base. So this is what it's starting to look like. So now we dump everything into storage, and then we have our data sets, and then our data sets can then pull from that storage and produce features. There's one big problem here, which is this is all in batch, right? So what that means is, are they going to be pulling our storage all the time and then pre-computing everything? I mean, that sounds pretty horrible. But we had done this with the knowledge of Spark 2. So we knew where Spark 2 was headed, and we knew that data sets would be a part of structured streaming so that we could then allow our data scientists to code in what they thought was batch mode, but then would transparently work for streaming. So this is kind of where we're at now, which is this meets all of the guidelines that we want. We have end-to-end type safety. We have ingestion that we believe is actually working reliably, and our data scientists aren't reliant on other people to be able to turn these things into production features. So before I stop, I want to make one comment, which is a lot of this talk today has been about what I would call sort of BI-style data analysis, right? It's very SQL heavy, and in terms of what it gives you back is it gives you back a clear picture of what's going on today, right? It's a way to go through your data and pull things out. I think that the obvious other piece of what's going on is prediction, machine learning, and there the core currency, instead of being SQL, is linear algebra, right? And you know, the thing I'm wondering about this is, will this actually work in that setting? And I think it's going to require something more. And the reason is because if you think about linear algebra from a typed point of view, it's essentially opaque to the compiler what's going on in there. It's just a tensor of floats, right? And to be able to get the same level of clarity that we have in a setup like this is going to take something additional. And that's kind of the next thing that we're looking at. So this has met the first series of requirements we have, but sort of going forward towards prediction, it's going to require sort of an additional step. So I will stop there and take questions. It's also worth mentioning again, if there are any Scala engineers who love to do data scientists, we're hiring. In
Boston?
In Boston. Alexi, if you have enough of them in California, we could be convinced to open up a West Coast office.
I didn't, but I might know some. I mean, I was just asking, how do data scientists kind of feel in this structure?
There was some initial resistance, especially when we moved from Panda to PySpark DataFrames. I think as soon as they got a taste of being able to have very homogeneous access across our data sources, they were really happy, because what they want is they want one enormous data frame that has everything they want, and then they can just go to town. But getting that is the hard part for them, and I think that Spark made it very easy for us to do that, and then they were on board. Now, sort of coaxing them towards Scala was a little easier because of how similar Spark and Scala looked, but it's still sort of a work in progress. I think that right now we've libraried away a lot of the complexity so that they can work in something that looks just like pure Spark without having to embrace the rest of Scala, and hopefully they'll kind of expand out from there.
Do you use MLlib in Spark?
We're starting to use MLlib more and more. And that's exactly my point about using machine learning and this sort of typed point of view. So if we want data scientists to be able to turn out features directly, we have to be sure that we know exactly what the algorithm is doing from a type point of view, right? And that's hard to know because we basically take in some clinical information, you project it into some space that doesn't necessarily make immediate clinical sense, and then you have to map it back to clinical reality, right? And it's very hard. You lose like any notion of what's going on in the middle there, and that's what makes the linear algebra part very challenging.
You mentioned some kind of database storage for intermediate results. I'm curious, why not just serialize DataFrames into Parquet?
I think this is basically a legacy issue. So we were making all of these decisions in motion, and a lot of it was what we had available at the time. So we already had, we had a lot of investment in MySQL, and we had a lot of investment in Cassandra and Elasticsearch. So it was just too easy to put it in there right away because, a few minutes to cook up the schema you want, and then all of a sudden you've got a place to put it.
All right. Well, thank you, Gopal.
Thank you.